And this chapter is known as wave-particle duality. In it we're exploring the nature of light, the question, what is light? Now, any time we've dealt with light up to now, we've dealt with it as a wave. But what we're going to see in this chapter is the idea that light can also act like a particle. So it can be a wave in some situations, some experiments, and it can be a particle in others. That's what we mean by wave-particle duality. I'm going to group together learning outcomes 1, 2 and 3. You can't really do one without the other. And we're just going to start by defining the photoelectric effect. So it's the removal of electrons from a metal surface using electromagnetic radiation. So generally light, but we'll look at other things like ultraviolet, infrared, stuff like that. So basically the experiment that we'll look at in class is when we shine light at a zinc plate which we've charged. And what we find is that only in one special situation when we're doing it in class, that when it's negatively charged plate, the plate's made of zinc, and when we shine ultraviolet light in it, we find that we can knock the charge off. Okay, so that we're knocking the electrons off of that surface. And now we're trying to explain what that, why that's important. So the photoelectric effect only occurs if the radiation being used has high enough frequency. And we'll come back later and define what we mean by high enough. And it doesn't matter how strong or how bright a source is, if it doesn't have a high enough frequency, it doesn't cause a photoelectric effect. And the opposite is true. If it's got a high enough frequency, it can be a really weak light source and it still causes it. So that can't be explained using a wave model. If light is a wave, then the energy would eventually build up and you'd be able to knock electrons off. So if you've got high enough intensity, if you let it run long enough, it would eventually knock electrons off. But this reminded scientists of experiments they did with particles. So if you fire a beam of particles at, for instance, electrons on the surface of a metal plate, then once they get to a certain energy, they can knock the electrons off. So it made them think of light as acting like a particle. And we call those particles of light photons. And each of those particles of light then carries a certain amount of energy. And what this means, if the photoelectric effect occurring, is it means that the individual photons have enough energy to eject an individual electron. So only one photon can act on an electron at a time. And this is like particles. Okay, so particles exist at a specific point in space. So you can't just kind of double them up like you can with waves. You can just make waves stronger, but with particles, they don't. So that gives us evidence for the particle nature of light. And because only one photon can interact with one electron at a time, photons which don't have enough energy cannot cause the photoelectric effect. And knock electrons off. Those electrons that are knocked off are sometimes called photoelectrons, just to confuse things a wee bit. Right, so you've got to kind of get that phrase clear in your head as distinct from photons. The photons are the particles of light that we can shine in. Photoelectrons are any electrons that are knocked off by that light. So in our previous description, we've linked the idea of photon energy to the frequency, and we've said that if it's got a high enough frequency, its photons will have high enough energy. And the equation which links that, this is a very simple one, E equals hf, so the energy is proportional to the frequency. E is the photon energy. H is called Planck's constant. It's given in the data sheet. And F is the frequency. The units of Planck's constant, incidentally, are joules per second. So, very simple example. Calculate the energy of a photon with frequency 6 times 10 to the 14 hertz. So visible light tends to be of that sort of order of magnitude, 10 to the 14 hertz. Usually between round about 4 times 10 to the 14 and 7 times 10 to the 14. When you get higher than that, you're going into ultraviolet light. So this 6 times 10 to the 14 would probably be somewhere round about blue. But very simple calculation then. You've got F. You can look up H, and it's 6.63 times 10 to the minus 34. So it's an incredibly small value, which is probably why we didn't notice this idea for so long, that basically the individual packets of energy in light are very, very small. But now we can use the formula. And get a simple answer. So, rounded to 3 significant figures is 3.98 times 10 to the minus 19 joules. And typical answers tend to be around about that, 10 to the minus 19, 10 to the minus 20. Obviously it depends which part of the electromagnetic spectrum you're in, so if you go towards gamma rays you're going to get higher energy, so that's why they're more dangerous. It's not about the total energy, it's the idea that they come in individual particles of energy which are bigger and can cause more harm. Compare that though with nuclear reactions, where you're maybe looking at 10 to the minus 14, 10 to the minus 15 joules. You can see they were significantly higher than these light interactions. And in 5 and 6 we define these simple terms, then the work function, or the other way around, the threshold frequency, of a metal, so this is a property of the material you're using. Is the minimum frequency of a photon required for the photoelectric effect. And it's often given the symbol F naught. And the equivalent energy is called the work function. And that therefore would be the minimum energy. I'll put in of a photon actually because it's a good habit to always refer to photons in your answers. That's the kind of key word that you're looking for. So you often see that as E naught, the kind of minimum. So the F naught refers to the minimum frequency, E naught to the minimum energy. And therefore, it's not really an outcome, but because E is always equal to HF, you can also use the idea then that E naught is H times F naught, so you can link the threshold frequency and the work function quite simply. And that idea then is important for the next learning outcome. So kind of putting that after 5 and 6. Lastly, for number 7, basically number 7 deals with the idea as, well, if that's a minimum energy, what happens if you put in a photon with an energy greater than that minimum energy? And what we find is that basically the excess energy that you've put in comes out as a kinetic energy of the electron that's getting knocked off. So if you put in more energy, then more than the work function, any excess comes out in the form of the kinetic energy of the electron. And the more energy you put in, the more kinetic energy the electron will have. So simple conservation of energy is that Ek is equal to the energy of the photon you put in minus the energy that's required to release the electron. But that's usually then written as HF minus HF naught for using the two equations we've just introduced. So that's how it appears in the formula sheet. So Ek is the kinetic energy of the emitted electron. And from that we can work out the speed of the emitted electron. Strictly speaking, it's a maximum speed because you can sometimes find that you get a wee bit less. So you'll often find in questions it refers to it as a maximum speed. H we've already defined as Planck's constant. So I should put up there, that's in joules. F is the photon frequency, so the photon that you're firing in, and F naught is a threshold frequency. And remember, that's a property of the metal that you're dealing with. So for instance, we use zinc when we do this experiment. It's got a threshold frequency in the ultraviolet region, so we can use ultraviolet to knock off the electrons. You can get materials with threshold frequencies in the visible region, but they're difficult to deal with in experiments because any normal light then can knock the electrons off, so you kind of get the electrons knocked off when you don't want them. But they can have other uses as well. So I'll do a worked example based on that. So in this we're given E naught, the work function. We're also given the wavelength of the light being used. and that's all we're given. Obviously, Planck's constant we can look up, and we'll find out later as well. We also need the mass of electron. So for part A, calculate the minimum frequency. So this is the threshold frequency we've been asked. And the relevant equation then would be E naught equals H F naught. Plug in your values. And we get F naught is 3.16 times 10 to the minus 19. That's our answer for part A. For part B, need to do a wee bit of revision. We're given a wavelength, but all our equations involve frequencies. So the first thing we're going to have to do is to work out the frequency of the incident light, the frequency of those photons going in. So for that, we'll also need the speed of light. Okay, not to be confused with the maximum velocity of the electrons we're going to work out in part C. Okay, you've got the light going in at the speed of light, and then the electrons coming out at various speeds. So first of all, we can use V equals F lambda. And that gives us the value of F as 5.09 times 10 to the 14 hertz. But that's not the final answer. The question we're actually being asked is a maximum kinetic energy. And the reason I was using the wavelength to work out the frequency is, remember, our maximum kinetic energy formula is given by that HF minus HF naught. So just plug in all the values. Now, one thing you've got to watch for, that you're always dealing with kind of consistent values. So don't you be dealing with frequencies and energies, not mixing them up. So if you've got a 10 to the 14, you can't be kind of adding that to a 10 to the minus 34. Or a 10 to the minus 19. That wouldn't make sense. So just watch that you're dealing consistently with energies or consistently with frequencies. I could put in the separate value of H and F naught here, but I know that HF naught, because that's what I use to work out F naught, I know that HF naught is the work function that we were given. Now putting all that in, we get that the maximum kinetic energy the electrons could have is that. They could have a wee bit less because they're attracted back by neighbouring electrons and stuff like that as well. And then we're going to use that value to do part C. So that's our EK. The mass of the electrons I'd written over the page from the data sheet as well. We're using that to work out V. So now we can use EK equals a half mv squared. Plug in our values. Rearrange for V squared. And then taking square roots. Okay, and as ever, you'd be worried if you're getting relativistic answers. So, certainly if you're getting greater than 3 times 10 to the power 8, you've made a mistake somewhere. Okay, so that's how we'd work out the velocity of the electrons being emitted. And lastly, some applications of the photoelectric effect. Probably the two that are easiest to talk about are, first of all, charge-coupled devices, or CCDs. And these are the sensors in digital cameras. So you've almost certainly got these in your mobile phone, for instance. And you get a small array of them, and that defines how many pixels you've got in your images. You can also use the photoelectric effect in light meters for photography. Right, and cinematography as well. The two kind of probably more everyday ones that you could come across. We also have a device called a photomultiplier tube. And its idea is to take kind of faint light signals and then use the photoelectric effect to amplify them. Right. So for example, they're used in gamma cameras that we met in Nat 5 as applications of radiation. And the last one, very similar sort of idea, is known as an image intensifier tube. And these are used in things like night vision. Okay, so similar sort of idea, working slightly different technology. And also in medical imaging, like the photomultiplier as well. Now lastly, not tied into a particular learning outcome, but I think it's probably worthwhile being familiar with a couple of graphs. If you, rather than just discharging the charge plates like we did in class, if you can gather the electrons as they are knocked off the plate, you can measure a current. And if you plot that current versus frequency, what you find is a shape something like this, where that value there is the threshold frequency. No emission takes place below that frequency. But above that frequency, as you increase it, what we find is that the kinetic energy of the electrons increases, but their speed increases with the square root of that kinetic energy, so you don't get a straight line increase in the current. So the speed of the electrons goes with the square root, so you get a curve graph beyond that point. And the other one, we'll do more on irradiance in the next unit, but basically it's a measure of how bright your light source is. So if your light source is causing the photoelectric effect, okay, so you're above the threshold frequency, then what we find is that the current is proportional to the irradiance, right? Straight line through the origin. Obviously, if you're below the threshold frequency, you don't get any current, so it would just be a flat line.